Let's give some motivation for diagonalization. Consider the Fibonacci sequence 0, 1, 1, 2, 3, 5, 8, 13, and so on. It can be defined inductively as follows. f0 equals 0, f1 equals 1, fk plus 1 equals fk plus fk minus 1 for all k greater than or equal to 1. In other words, after defining the first two terms, 0 and 1, each next term is obtained by adding the previous two terms. It is a natural question to ask whether we can find an explicit formula for fk. To do so, let's observe that we can write the inductive definition in matrix form as follows. The vector fk plus 1, fk, equals the vector 1 times fk plus 1 times fk minus 1, 1 times fk plus 0 times fk minus 1, which equals the matrix 1, 1, 1, 0 times the vector fk, fk minus 1. So this equals A times the vector fk, fk minus 1, where A is the matrix 1, 1, 1, 0. In other words, we can write the vector with two consecutive terms as a matrix times a vector with two other terms, where both indices of the two terms are decreased by 1. We can repeat this to get that the vector fk plus 1, fk, equals A squared times the vector fk minus 1, fk minus 2, and so on, until we have A to the power k times the vector f1, f0, where f1 and f0 are 1 and 0 respectively. So, in order to find an explicit formula for fk, it boils down to computing A to the power k for each positive integer k. This is not always an easy task, except for a special kind of matrices, called diagonal matrices. The definition of a diagonal matrix is as follows. An n by n matrix D is called diagonal if all entries below the main diagonal of D are 0. In other words, D takes the following form, where the main diagonal entries are D1, D2 up to Dn. In this case, we write D equals diag bracket D1, D2 up to Dn. As a quick example, the 0 matrix and the identity matrix are diagonal matrices. Before we discuss the properties of diagonal matrices, we need the following definition. Let P of x equals lambda n times x to the n plus lambda n minus 1 times x to the n minus 1 plus all the way to lambda 1 times x plus lambda 0 be a polynomial, where lambda n minus 1 up to lambda 0 are real numbers, and A be a square matrix. We define P of A equals lambda n times A to the n plus lambda n minus 1 times A to the n minus 1 plus all the way to lambda 1 times A plus lambda 0 times I. This is the definition of a polynomial of a matrix, where we replace the variables by the matrix A, and the constant term lambda 0 is replaced by lambda 0 times I. Now, let's discuss the properties of diagonal matrices. Firstly, if we have a diagonal matrix D1, D2 up to Dn, plus a diagonal matrix K1, K2 up to Kn, then the resultant matrix is also diagonal, with main diagonal entries D1 plus K1, D2 plus K2 up to Dn plus Kn. In other words, if we add two diagonal matrices, the resultant matrix is also diagonal, where the main diagonal entries are the corresponding sums of the main diagonal entries of the two diagonal matrices. To prove this, let A be the first diagonal matrix and B be the second diagonal matrix. Then A equals the matrix with entries Aij, where Aij equals Di if I equals j and 0 otherwise, and B is the matrix with entries Bij, where Bij equals Ki if I equals j and 0 otherwise. Hence, the ij entry of A plus B is Aij plus Bij, which equals Di plus Ki if I equals j and 0 otherwise. So, A plus B equals the diagonal matrix with main diagonal entries d1 plus k1, d2 plus k2, up to dn plus kn. The second property is that if we multiply a diagonal matrix d1, d2 up to dn by a real number, lambda, the result is also a diagonal matrix with main diagonal entries lambda times d1, lambda times d2, up to lambda times dn. To prove this, we let A with entries aij be the first diagonal matrix as before. Then the ij entry of lambda times A is lambda times aij, which equals lambda times di if I equals j and 0 otherwise. So lambda times A is the diagonal matrix with main diagonal entries lambda times d1, lambda times d2, up to lambda times dn. For the third property, if we multiply a diagonal matrix d1, d2 up to dn by another diagonal matrix k1, k2 up to kn, then the result is also a diagonal matrix with main diagonal entries d1 times k1, d2 times k2, up to dn times kn. In other words, if we multiply two diagonal matrices, we just need to multiply the corresponding main diagonal entries. To prove this, let A with entries aij be the first matrix, and B with entries bij be the second matrix. Now, aim times bmj equals di times ki if I equals m and m equals j, and 0 otherwise. So, the ij entry of A times B is ai1 times b1j plus ai2 times b2j plus all the way to ain times bnj. Since I equals m and m equals j means that I equals j, the sum is only non-zero if I equals j, and it is equal to di times ki. Hence, A times B is a diagonal matrix with main diagonal entries d1 times k1, d2 times k2, up to dn times kn. For the fourth property, if we raise a diagonal matrix d1, d2 up to dn by a power m, the result is a diagonal matrix with entries d1 to the power m, d2 to the power m, up to dn to the power m, for all positive integers m. We will prove this by induction on m. M equals 1 is true, because it just means that the diagonal matrix equals itself. Now, assume inductively that for some positive integer t, the diagonal matrix d1, d2 up to dn to the power t equals the diagonal matrix d1 to the t, d2 to the t, up to dn to the t. Let's call this star. Then, the diagonal matrix d1, d2 up to dn raised to the power t plus 1 equals the diagonal matrix d1, d2 up to dn raised to the t times the diagonal matrix d1, d2 up to dn. By star, the first diagonal matrix becomes the diagonal matrix d1 to the t, d2 to the t, up to dn to the t. Now, using the third property, we may multiply the corresponding main diagonal entries to get the diagonal matrix with entries d1 to the t plus 1, d2 to the t plus 1, up to dn to the t plus 1. The fifth property states that the determinant of the diagonal matrix d1, d2 up to dn equals the product d1, d2 up to dn. Observe that a diagonal matrix is automatically a triangular matrix, and triangular matrices has the property that its determinant is equal to the product of the main diagonal entries. For the sixth property, if d1, d2 up to dn are all non-zero, then the diagonal matrix d1, d2 up to dn is invertible, and its inverse is the diagonal matrix d1 to the negative 1, d2 to the negative 1, up to dn to the negative 1. Using the third property, the diagonal matrix d1, d2 up to dn times the diagonal matrix d1 to the negative 1, d2 to the negative 1, up to dn to the negative 1 equals the diagonal matrix d1 times d1 to the negative 1, d2 times d2 to the negative 1, up to dn times dn to the negative 1. So we have the diagonal matrix with main diagonal entries all equal to 1, which is the identity matrix. Similarly, if we swap the order of the two diagonal matrices, we get again the identity matrix. As the last property, if P of x is a polynomial, then P of the diagonal matrix d1, d2 up to dn equals the diagonal matrix with main diagonal entries P of d1, P of d2 up to P of dn. To prove this, let P of x equals the sum from m equals 0 to n of the terms lambda m times x to the m, where lambda m are real numbers. Let A be the diagonal matrix d1, d2 up to dn. For each m equals 0, 1, 2 up to n, A to the m equals the diagonal matrix d1 to the m, d2 to the m up to dn to the m, by the fourth property. So, lambda m times A to the m equals the diagonal matrix lambda m times d1 to the m, lambda m times d2 to the m, up to lambda m times dn to the m, by the second property. This implies that P of A equals the sum from m equals 0 up to n of lambda m times A to the m. This equals the sum from m equals 0 up to n of the diagonal matrix lambda m times d1 to the m, lambda m times d2 to the m, up to lambda m times dn to the m. This is a sum of diagonal matrices, so by the first property, we have the diagonal matrix with main diagonal entries, the sum of lambda m times d1 to the m, the sum of lambda m times d2 to the m, up to the sum of lambda m times dn to the m, where each sum is from m equals 0 up to n. Observe that the sums are values of the polynomial at d1, d2 up to dn.